Hi all, as you can see here, we will have a quick revision of the chapter Electricity. We will be discussing about current, voltage, resistance and power. When we think of electricity, the first term is electric circuit. Electric circuit is any closed and continuous path through which current flows. Now, let's see what is electric current. Electric current is represented using the letter I. I is equal to Q by T. Actually, current means the amount of charge flowing through a particular area in a given unit time. It's called electric current. I'll just show you. Consider this small area through which the charges are flowing. So, how many charges are flowing through this particular area in a given time? That's called the current. That's why we write I equals Q by T. Here, the SI unit of current is ampere. The SI unit of charge is coulomb. And the SI unit of time is second. So, 1 ampere is when 1 coulomb of charge is passing through a circuit in 1 second. So, 1 ampere is 1 coulomb by 1 second. The instrument that is used to measure current is called ammeter. Instrument is called ammeter. In a circuit, the direction of flow of current is always taken from positive to negative. It's always taken from the positive terminal to the negative terminal of the cell. Just see here. As you can see here, in this cell, the charges are flowing from positive terminal to the negative terminal. So always, by convention, the direction of flow of current is taken from positive terminal to the negative terminal. Now let's discuss a little bit more about this part. Electric current is actually flow of charges. Here, the charge that flows is electron. It's the flow of electrons. We know the charge of an electron is 1.6 into 10 raised to minus 19 coulomb. 1.6 into 10 raised to minus 19 coulomb. At the same time, we know charge of proton is also 1.6 into 10 raised to minus 19 coulomb. The difference is electron is negatively charged and proton is positively charged. Just now we told that electricity is flowing from, or current is flowing from positive to negative. And we also told that it's the flow of electron. Electron is negatively charged. Then how will it go from positive to negative? It should go from negative to positive, right? It is because when scientists started studying about electric current, first they believed that electricity is the flow of proton. But later they found out that it's the flow of electron. So initially when they thought like it's the flow of proton, they kept the direction of current from positive to negative. Later, even though they found out that it's the flow of electron, they didn't change the rule that they made. So now by convention, the direction of flow of electric current is always taken from positive to negative. We told that electricity is the flow of charges. Here, charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. It's a very minute value. It means 0.00000, so many zeros and 1/6. So it's a very minute value. We told the SI unit of charge is coulomb. Then here we wrote 1 coulomb. Then what is 1 coulomb? How many electrons are needed to make 1 coulomb charge? In order to make 1 coulomb charge, we want 6 into 10 raised to 18 electrons. So 6 into 10 raised to 18 electrons makes 1 coulomb of charge. We want so many electrons to make 1 coulomb of charge. Here we told that the SI unit of current is ampere. but we have smaller units of current as well. We have milliampere and microampere. Milliampere is 10 raised to minus 3 ampere. Microampere is 10 raised to minus 6 ampere. So when we want smaller units of current, we'll take milliampere and microampere. Now let's see what is potential difference. Potential difference is actually the work done to take a unit charge from one point to the next point in the circuit. In this simulation, if we have to take a charge from this point to this point, the work done to take this charge from this particular point to the next point is called potential difference. So if needed, I'll increase the potential difference of this. So when I increase the potential difference, actually the work done is increasing. So I'll be able to do more work. Just observe, I'm increasing the potential difference. I'm making 9 volt to 11 volt, 12 volt. I'm making it more. When I increase the potential difference, you can see the bulb is glowing more and the charges are also moving faster. So potential difference is the work done to take a unit charge from one point to the next point. Potential difference is represented using the letter V. As I told you, potential difference is work done on a charge to take it from one point to the next point. So it can be written as V is equal to W by Q. The SI unit of potential difference is volt. The SI unit of work done is Joule. And the SI unit of charge is Coulomb. So 1 volt is 1 Joule per 1 Coulomb. Now we have studied about current and potential difference. So we have a rule relating both, that is Ohm's law. Ohm's law states that potential difference is directly proportional to current in a given circuit. I can write it like V directly proportional to I, or V is equal to I into R. Here we have a constant, that constant is R. This constant R is called the resistance. Resistance is nothing but something that resists the flow of current. The SI unit of resistance is ohm. The SI unit is ohm, which is usually represented using the symbol ohm. To remember Ohm's law, let's make a triangle here. Inside the triangle, we'll write V, I, R in this order. So V is equal to I into R. R is equal to V by I. I is equal to V by R. This is one of the main equations that we should remember in this chapter. So the mathematical statement of Ohm's law is V directly proportional to I, where V is equal to I into R. R is the resistance. SI unit of resistance is ohm. According to Ohm's law, when we draw a graph between V and I, it will be a straight line. This graph also shows Ohm's law. Now let's focus more on resistance. From this Ohm's law, let me write R is equal to V by I. Let's see what is 1 ohm. The SI unit of resistance is ohm. So 1 ohm is equal to SI unit of voltage, SI unit of potential difference is volt. 1 volt by 1 ampere. SI unit of resistance is ohm, potential difference is volt, current is ampere. So 1 ohm is equal to 1 volt by 1 ampere. So in Ohm's law, V is directly proportional to I. V is directly proportional to I. When I increase V, I will also increase. when I decrease V, I will also decrease. Now, let's see the factors which will decide the resistance. Resistance R is equal to rho L by A, which means resistance is directly proportional to the length of the material, it's inversely proportional to the area of the material, and it's directly proportional to rho. Rho is nothing but the nature of the material. If the material is iron, the resistance will have a particular value. The resistance in gold will be different from the resistance in silver. That will be different from the resistance in iron. So, resistivity, rho stands for the nature of material. L stands for the length of the material. A stands for the area of the material. So, when length increases, resistance increases. When area increases, resistance decreases. When resistivity increases, resistance increases. In Ohm's law, there is a statement at the end of it. It is nothing but potential difference is directly proportional to current in a given circuit, given that the temperature remains constant. If temperature changes, all the values will change. So, resistance depends upon resistivity, length of the material, area of the material, and temperature. I told you resistivity stands for the nature of material. So, for a particular material, resistivity will be a constant value which will not change. So, if the length of the material changes or area of the material changes, doesn't matter, it will not affect the resistivity of the material. But if the temperature changes, then resistivity also changes because the nature of the material changes. It's no more that material. That's why. So, just remember one important point that resistance will keep on changing depending on resistivity, length, area, and temperature of the material. But resistivity is always a constant value. It will only change when the temperature changes. Now let's see the two types of connections that come under the resistors. One is series connection and the other one is parallel connection. If I have two resistors here, in series connection, I'll connect my resistors like this. Suppose my first resistance is R1 and second one is R2. Here, in parallel connection, I'll connect my resistors like this. This is my R1 and this is my R2. Now, the effective resistance of series connection is given as Rs is equal to R1 plus R2. Suppose here my resistance is 1 ohm and here if it is 2 ohm, I'll just add both. That is my overall resistance. That is my effective resistance. So 1 plus 2 gives 3. Here, in the case of parallel connection, the equation is slightly different. That is 1 by Rp is equal to 1 by R1 plus 1 by R2. So if I have two resistors there, then I should take the reciprocal of it. One more main thing is, at the end of the equation, don't forget to take the reciprocal again. Now I am not finding out Rp here, I am finding 1 by Rp. So at the end, please take the reciprocal, only then you will get Rp. Remember one more important point, that in series connection, current is always same. In series connection, current is same. In parallel connection, voltage or potential difference is always same. So in the case of series connection, potential difference will be different. In the case of parallel connection, current will be different. So in series connection, current will be same, voltage will be different. In the case of parallel connection, voltage is same, current is different. Just remember that in the case of parallel connection, voltage is always same. In our houses, the connection that we have is parallel connection. That's why we are getting same voltage for all the equipments. Next is heating effect of electric current, also known as Joule's law of heating. Joule's law of heating. The mathematical statement of Joule's law of heating is H is equal to I square RT. According to Joule's law of heating, whenever current passes through something, it produces heat. When you keep your mobile phone for charging, after it gets charged, you will feel that the charger has got some heat, or your iron box is working based on the heating effect. So Joule's law states that whenever current passes through something, it becomes hot. So according to this, the heat or the heat energy made in an electrical equipment depends upon the square of the current, the resistance, and the time in which the current is passing. So if the time increases, then the heat will increase. If the resistance increases, the heat will increase. Again, if the current increases, then the heat will increase. If the current doubles, then the heat will become 4 times, because current is the main factor there. It is square times. We have few other equations also for the heating effect of electric current. From Ohm's law, we have I is equal to V by R. If we make the value of I as V by R here in this equation, then we get H is equal to V square by R square into R into T. Here R and square get cancelled. So H is equal to V square by R into T. This is another equation for the heat generated in an electrical equipment. Now in the same equation, instead of R, from Ohm's law, R is equal to V by I. If I give R is equal to V by I, then I will get H is equal to I square V by I into T. So here I and I will get cancelled. We will get H is equal to V into I into T. This is another equation for the heat generated. H is equal to V into I into T. Next is electric power. We know the general equation of power. Power is equal to work done by time. We also know that work done is same as energy. So power is energy by time. Here the energy is the heat energy. Heat energy by time. Or we can even write like power is equal to, we know the equation for heat. H is equal to I square RT divided by time. Here time and time will get cancelled. So we got power is equal to I square R. This can be one equation of power. Power is equal to I square R. Now as we did earlier, from Ohm's law we know that I is equal to V by R. I'll give this equation here. So instead of I, I'll write V by R. So power is equal to V square by R square into R. So R and R will get cancelled. We will get P is equal to V square by R. This is another equation for power. So power is equal to V square by R. Now, as I did just now, instead of R, from Ohm's law, R is equal to V by I. I'll equate R here. So power becomes, power is equal to I square into V by I. I and I will get cancelled here. So power is equal to V into I. So here I got the third equation for power, that is power is equal to V into I. In the previous slide, we wrote the equations for heat. Let's go back to the previous slide. Here, we have an equation H is equal to V into I into T. In the present slide, we got an equation that P is equal to V into I. Power is V into I. I'll equate this one in the previous slide where V into I came. So here I'll write H is equal to V into I is power. So power into time. This is another equation for heat. So now I got three equations for heat. First equation is the Joule's law, that is H is equal to I square RT. Second equation is H is equal to V square by R into T. Third one is H is equal to V into I into T. Next one is H is equal to power into time. So based on situations, we'll have to use this. Sometimes they'll give you the time and the power, and you will have to find out the heat. So use this equation. Sometimes in the question, it will be given the potential difference, the current and the time will be given. So use this equation to find out the heat. As you know, the unit of power is watt, represented using the capital letter W. So SI unit of power is watt. Watt also has higher units, that is kilowatt, represented using the letter kW. So SI unit of power is watt, its higher unit is kilowatt. If we go back to the previous slide, here we know the SI unit of heat energy is Joule. It is Joule, represented by the letter capital letter J. Here, since we got the equation heat is equal to power into time and time plays a major role in electric current, here for heat generated, we can even have one more unit, that is watt hour. Here SI unit of power is watt and time is hour. So watt hour is a unit to represent the energy generated by electrical equipments. The higher unit of watt hour is kilowatt hour. Higher unit is kilowatt hour. So 1 kilowatt is same as 1000 watt. Since kilo stands for 1000, 1 kilowatt is same as 1000 watt. Please do remember one more important point, that is kilowatt hour, which is one of the units of heat energy generated in electrical equipments. If it is 1 kilowatt hour, this 1 kilowatt hour is called 1 unit. 1 kilowatt hour is called 1 unit. In our electricity bill, usually it will be represented as units consumed. So when they write 1 unit there, they mean we have already consumed 1 kilowatt hour of energy. So when we get electricity bill, they'll count the number of units and they'll multiply it with the amount for a single unit. So usually for the exams, they will give us some question. They'll ask us to find out the energy consumed and they'll ask us to find the amount for the energy consumed. So during that time, we'll have to convert the energy into kilowatt hour and we'll have to multiply with the amount given. So thinking of electricity, circuit is a complete and closed path through which current passes. Current is the amount of or the number of charges passing through a particular area in a given unit time. So 1 ampere is equal to 1 coulomb per 1 second. We told it's the flow of charges. So here electrons or protons will be flowing. So here the direction of current is taken as positive to negative. It's the flow of electrons. Charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. Charge of proton is also same. This is negatively charged. This is positively charged. Then to make 1 coulomb of charge, we need 6 into 10 raised to 18 electrons. Ammeter is the instrument used to measure current. SI unit is ampere. We have smaller units called milliampere and microampere. 1 milliampere is 10 raised to minus 3 ampere. 1 microampere is 10 raised to minus 6 ampere. Coming to potential difference, it is represented using the letter V. Voltage is the SI unit of potential difference. Potential difference is actually the work done to take a unit charge from one point to the next point. The work done on the charge. That is called potential difference. 1 voltage is 1 joule per 1 coulomb. Potential difference is measured using the instrument called voltmeter. Voltmeter is the instrument used to measure potential difference. Now we have Ohm's law. Ohm's law states that the potential difference is directly proportional to the current in a given circuit, given that the temperature remains constant. So V is equal to IR. Here we have a constant value, that is R. It's called resistance. Resistance is nothing but the resistance offered to the electric current. So the SI unit of resistance is ohm, represented using this symbol. Looking at this triangle, we'll be able to remember the Ohm's law and the equations related to that easily. V is equal to I into R. I is equal to V by R. R is equal to V by I. This is the graph for Ohm's law. It will be a straight line graph. Then 1 ohm is 1 volt by 1 ampere. Now coming to resistance. Resistance R is equal to rho L by A. Here rho is the nature of the material, L is the length of the material, A is area of the material. Remember that resistance will keep on changing, but resistivity is a constant value which will not change. But both of them will change with temperature. If temperature changes, both of them will change. Usually there will be questions related to resistance and resistivity. Resistivity is a constant value which will not change. Keep it in your mind. Now, when we connect the resistors, we can connect them in two different ways. One is series connection and the other one is parallel connection. In series connection, just keep on adding the resistors. In parallel connection, take the reciprocal and then add it. So if you are given two different resistors, you will get the maximum resistance in the case of series connection. So series connection gives you a maximum resistance and minimum resistance will be offered by parallel connection. Suppose you have two 2 ohm resistors. In the series connection, you will add it. You will get 2 plus 2. You will get 4 ohm. In the case of parallel connection, you will take 1 by 2 plus 1 by 2. You will get 1. Reciprocal of 1 is also 1. So you will get 1 ohm. So here, in parallel connection, you will get the minimum resistance. And in series connection, you will get the maximum resistance. Now, in series connection, current will be always same. In parallel connection, voltage will be always same. Next is heating effect of electric current, which is also known as Joule's law of heating. The mathematical statement of Joule's law of heating is H is equal to I square RT. When we use Ohm's law and rearrange the equation, we'll get other equations as well. H is equal to V square by R into T. H is equal to V into I into T. H is equal to power into time. As we told earlier, heat is a type of energy. SI unit of any energy is Joule. In the case of electricity, heat can be calculated as power into time. SI unit of power is watt and SI unit of time is hour. So, SI unit of energy here in the case of electric circuits can be watt hour also. Its higher unit is kilowatt hour. 1 kilowatt hour is same as 1 unit. This is used for calculating the electricity bills. Then 1000 watt is same as 1 kilowatt. Next was power. As we know, power is work done by time. From all that we got power is equal to I square R in the case of electric circuits. Also, rearranging the equation using Ohm's law, we got power is equal to V square by R. Again, power is equal to V into I. SI unit of power is watt. Its higher unit is kilowatt. The next topic is about magnetic effect of electric current. Whenever current passes through any electrical device, it will create a magnetic field around it. If you take a magnetic compass and keep it near to a current carrying conductor, the magnetic compass shows deflection, which proves that whenever current passes, it creates a magnetic field, or the conductor behaves like a magnet. So, when you take a magnetic compass near to any current carrying conductor, it shows deflection. Observe here, the magnetic needle is showing deflection because even the needle is made of a small magnet. Let's see the properties of a normal bar magnet. A bar magnet has two poles. One is north pole and the other one is south pole. So a magnet has two poles. The area around a magnet where its influence is experienced is called magnetic field. The direction of magnetic field is always taken as north to south. Direction of magnetic field is from north to south. Any two magnetic field lines will never intersect each other. They won't touch each other. Then, degree of closeness of magnetic field lines will tell us how strong the magnetic field is. When we go away from the magnet, we know that the magnet will have less impact or less power. So, when we go away from the magnetic field lines will be more far away from each other. The gap between them will increase, which shows that the power is getting reduced. So, whenever we see magnetic field lines very much near to each other, it means that they have high power. Or if the magnetic field lines are very much far away, then it shows that the magnet has less power or the magnetic field has less power. So the strength of a magnetic field is decided by the degree of closeness of magnetic field lines. Now let's see how will be the magnetic field and the magnetic field lines created by different equipments. Suppose we have a long straight current carrying conductor. If we insert this current carrying conductor into a piece of paper and if we pour some iron fillings on top of this paper, we will see that it will make concentric circles here around the current carrying conductor. There will be lot of circles and the circles will be very much close near to the current carrying conductor, but when we go far away from it, the circles will go wider and wider. The distance between each circle will increase. This shows that the magnetic field strength is decreasing. So near to the current carrying conductor, the circles will be very much close. When it go far away, the circles will go away from each other. Now suppose if we take this long current carrying conductor and make it into a big loop and it is connected to a cell. Now we insert a piece of paper here in this area. So here we have a hole, again here also we have a hole. So on both the sides, here it behaves like a long current carrying conductor. Here also it behaves like a straight current carrying conductor. So here, as we saw earlier, we will have concentric circles. This side also we will have concentric circles. But at the center we will have a straight line. When we put iron fillings on top of it, this will be the pattern that will be visible for us. Now let's take a long insulated copper and we will make a cylindrical shape out of it like this. This is called a solenoid. Solenoid is very special to us because when we connect the solenoid to a cell and when the current passes through it, the solenoid also behaves like a magnet. If we pour iron fillings on top of it, we will be able to see similar pattern that we see in the case of a bar magnet. So direction of magnetic field here also will be from north to south. Inside the solenoid, the direction of magnetic field will be from south to north. There is one more important point. Inside the solenoid, the magnetic field lines will be parallel, which shows that inside the solenoid, the magnetic field is constant. It will not change. Here, even in the case of bar magnet also, the direction of magnetic field line inside the bar magnet is from south to north. So this forms a complete closed path. So outside the bar magnet, the direction is from north to south. Inside it is from south to north. Same way, in solenoid also, outside the solenoid, the direction of magnetic field will be from north to south and inside it will be south to north, and inside a solenoid the magnetic field will be a constant. And in the case of bar magnet, the poles of the bar magnet will have more power. The iron fillings will be mostly attached to the poles of the bar magnet. It shows that most of the power of the bar magnet lies towards the poles. Now, when we discussed about solenoid, I have been telling you that the direction of magnetic field will be from north to south. But how will we understand which is north and which is south? Before saying this, let's see the case of a straight current carrying conductor. In the case of a straight current carrying conductor, whenever current is passing through it, a magnetic field like this will be made. So how will we understand the direction of magnetic field? For that, we have right hand thumb rule. According to right hand thumb rule, imagine holding a current carrying conductor in your right hand in such a way that the thumb point towards the direction of current. Then your wrapped fingers will show the direction of magnetic field. This law is also called corkscrew rule, Fleming's corkscrew rule. When you open the cap of a bottle, you will rotate it towards left side and the cap will come up. When you close it, you will rotate it towards right side and the cap will go down. Something similar is happening here also. If the direction of current is in this direction, then your magnetic field will be like this. When you look from top, it is anti-clockwise direction, and when you look from bottom, it is clockwise direction. So right hand thumb rule helps you understand the direction of magnetic field or the direction of current. If the direction of current is given, you will be able to find out the direction of magnetic field. If the direction of magnetic field is given, you will be able to find out the direction of current. Now, how will you understand the direction of magnetic field, or how will you understand the north and south poles in the case of a solenoid? You already know that current will always flow from positive to negative. So, once if the current is going like this, you see the direction in which the current is going. Let's observe from this direction. When you observe from this side, if you see that the current is flowing in clockwise direction, then that is your south pole. When you observe from here, if you see that the current is flowing towards anti-clockwise direction, then that's your north pole. This is the easy trick to remember. You just come to any one of the sides and observe it, or you imagine like you're observing. So when you look from this side, if you feel like the current is flowing in clockwise direction, then it is your south pole. When you look, if the current is flowing in anti-clockwise direction, then that's your north pole. You just write N like this and S like this. Give arrow marks at the end. So in the case of south pole, this is always moving in clockwise direction. In the case of north pole, it's moving in anti-clockwise direction. So that you will be able to identify which pole is it. To increase the power of a solenoid, you can do different things. Either you can increase the number of turns of the solenoid, or you can increase the current passing through the solenoid, so that you will be able to increase the power or the magnetic field around the solenoid. Now you know that if current passes through any current carrying conductor, then magnetic field will be created. So suppose if a current carrying conductor is there, and if you keep one more magnet next to it, a U-shaped magnet. Suppose this is north pole and this is south pole. The direction of magnetic field will be from north to south. And you are introducing a current carrying conductor here, which is connected to a cell. In this also, current will be flowing. If this is positive and this is negative, current will be flowing from positive to negative, like this. So, here you will have a magnetic field. Here you will have one more magnetic field. So in this case, both the magnetic fields will interact each other, and this hanging material will move towards one direction. How to find out that direction? This can be done with the help of Fleming's left hand rule. So here we have the magnetic field created by the magnet. We have the direction of current, and we are going to find out in which direction will the object move. So for that, use your left hand. Here the long middle finger shows you the current. Remember that the chapter is all about current. So the long one stands for current. Your index finger shows magnetic field. Current is always related to magnet. So this one shows magnetic field. This one shows your thumb, which is little thicker one, little fat one. This one shows you the force or the direction in which the current carrying conductor moves. Make sure all the three fingers are mutually perpendicular to each other in such a way that your middle finger point towards the direction of current, your index finger point towards the direction of magnetic field, and your thumb will show you the direction of force. Remember that we'll get maximum displacement or maximum effect when all the three are mutually perpendicular to each other. That's why in Fleming's left-hand rule, it's told that all the three fingers should be mutually perpendicular to each other. Then they'll ask you different questions like the magnetic field is in this direction, current is in that direction, then in which direction will the object move, or in which direction will the current carrying conductor move. Then you please keep your fingers according to the question and you will get the answer. Sometimes instead of giving the direction of current, they will tell you an electron is entering in this direction. Remember that direction of current is from positive to negative. Direction of current is from positive to negative. If an electron is entering, it will always go to positive. So, if they tell you an electron is entering from left to right, then take the direction of current from right to left. Take the opposite. Suppose if they tell you a proton is entering, proton is positively charged, so it will always go towards negative. That is same as the direction of current. So if they tell you a proton is entering in this direction, then take the direction of current also as same. Our next topic is domestic electric circuits. In our house, the type of current that we have is AC, that is alternating current. The current that we get from cell or battery is DC. The advantage of AC over DC is AC can be transmitted over long distances without losing power or without losing energy. So in our houses, what we have is AC, which is alternating current. Remember that the frequency of AC is 50 Hertz. The frequency is 50 Hertz. In our houses, the voltage or the potential difference of AC is 220 volt. 220 volt. The current that we receive usually is 5 ampere. You might have seen some switches on which red lines are there or extra writings are there, which is used for washing machines and all. So in such switches, the current that we have is 15 ampere. When we look into a normal electric circuit, we will always have parallel connection. As we told earlier, parallel connection is better because if one equipment get fused, others will not be affected. Again, all the equipments will get equal voltage. Then you will be able to operate each equipment differently using switch. Suppose if it is series connection, all these will not be possible. In our houses, we'll be using wires of 3 different colors for wiring. First one is red, next is black, and the next one is green. Here, red wire is the positive, or it is called the live wire. Black is negative, or it is called neutral wire. Green is the earth wire. Remember that the switch or the fuse is always connected to the live wire. The switch or the fuse is connected to the live wire. Earthing is done with the green wire. In the plug, you will see something like this. On top, you will see a big metallic thing that is connected to the earth wire. This is usually done on metallic electrical equipments because when we have a metallic outer covering, there are chances for the current to leak onto the metallic body, and when we touch it, the current will pass through our body and we will get electric shock. In order to avoid this, from the metallic bodies, we connect a wire which has less resistance and it is taken to the ground. We know that current always takes the path with low resistance. So rather than passing through our body, the current will pass through this earth wire. So earth wire acts as a protector. There is one more important equipment used in wiring, that is fuse. When excess current passes through the electrical equipments, there are possibilities for the equipments to get fused. There we use fuse. Fuse actually works on the heating effect of electric current. When excess current passes through the fuse wire will melt and break the circuit so that excess current will not reach the equipments and we will be able to save the equipments. The same happens when there is overloading or short circuit. We saw the magnetic effect of electric current. Whenever current passes through any equipment, a magnetic field is created around the equipment. It was accidentally discovered by Hans Christian Ørsted. Coming to a bar magnet always has two poles, north pole and south pole. The like poles repel each other, unlike poles attract each other. The direction of magnetic field is taken as north to south. Inside a bar magnet, the direction is from south to north. No two magnetic field lines will intersect each other. The degree of closeness of magnetic field lines shows how strong the magnetic field is. When current is passed through a straight current carrying conductor, magnetic field lines will be made in the form of concentric circles. The degree of closeness of these field lines will increase when it moves away from the current carrying conductor. The direction of magnetic field can be found out using right hand thumb rule. So if you know the direction of magnetic field, you will be able to find out the current. Or if you know the direction of current, you will be able to find out the direction of magnetic field lines using right hand thumb rule. So right hand thumb rule shows a relation between magnetic field and current. Solenoid behaves similar to a bar magnet. The magnetic field lines also shows similarity. To find out the north pole and south pole of a solenoid when current is passed through it, use this trick. Come to any one side of the solenoid and observe the flow of current. If the current is flowing in clockwise direction, then that pole is south pole. If the current is flowing in anti-clockwise direction, then that pole is north pole. If there are two magnetic fields, one created by a magnet and the other one created by a current carrying conductor, then both the magnetic fields will interact each other and the current carrying conductor will show deflection or movement. This deflection or movement can be found out using Fleming's left-hand rule. Here, the middle finger shows the direction of current, your index finger shows the direction of magnetic field, and thumb shows the direction of motion. Direction of current is always from positive to negative. If an electron is entering from left to right, the direction of current is right to left. If a proton is entering from left to right, take the direction of current also same. In domestic electric circuits, the connection is always parallel. Parallel connection has a lot of advantages over the series connection. The current that reaches our house is AC current. AC has an advantage over DC, that is, it can travel long distances without getting any energy loss. The frequency of AC is 50 Hz, the potential difference is 220 volt, the normal current is 5 ampere. For special equipments, the current is 15 ampere. We have three different colors of wires. Red color stands for positive or live wire, black is negative or neutral wire, green is earth wire. Red wire is usually connected with switches and fuse. Green wire is the earth wire, which can save us from electric shocks. Electric fuse works on the principle of heating effect of electric current. Hope this video helped you really well in revising electricity topic. Thank you.